Happy Thanksgiving, everybody. When you come back from the Thanksgiving break on November 28, which is Monday, we'll make a smooth transition from Newton's first law to Newton's second law by doing the friction and friction graph. So make sure you have a good understanding on friction and friction graph before November 28, which is Monday. On Tuesday, November 29, we will do the Newton's second law. Once we make a smooth transition on November 28, on November 29, we're going to move forward to do free body diagram, this time not on Newton's first law, but also Newton's second law. So for example, let me remind you the free body diagram of Newton's first law and show you the difference between first law and second law. This is the Einstein. Let's say I want to move Einstein with constant velocity, and there, as you know, there must be some friction on the desk. So what do? You want to move Professor Einstein with constant velocity. You pull it by applying some force, and as you see, Professor Einstein is moving with constant velocity. How can you draw a free body diagram? Before you draw the free body diagram, you should understand that although Professor Einstein was moving, but since he was moving with constant velocity, this is an example of Newton's first law. Why is that? Let's first draw Professor Einstein. Alright, so you know that I apply some force to move Professor Einstein, and you saw he was moving with constant velocity. Now, right now, there is only one force applied to Professor Einstein. This body is in acceleration, but I said it's constant velocity. So there must be some other forces acting in other direction. Of course, that would be the force of friction. So let's put the force of friction. And force of friction has to be equal in magnitude, opposite in direction. Otherwise, there would be an acceleration at the x direction. And I said there is no acceleration at the x direction. So the applied force must be equal in magnitude and opposite in direction with the force of friction. Now, force of friction cancel with the applied force, and applied force cancel with force of friction. So what is the net force at the x direction? Of course, 0. So Professor Einstein therefore moves with constant velocity. Understand, you don't need net force more than 0 to move with constant velocity. Once you have net force more than 0, then you accelerate. You no longer move with constant velocity. Remember, this is Fg and this is Fn, which is equal in magnitude, opposite in direction. So this is Newton's first law, and acceleration, of course, is 0. So this is Newton's first law. Now let's show you Newton's second law. And make it to allow you to see the difference. Okay, to see the Newton's second law, I'm going to start moving Professor Einstein. Applied force is much bigger than, of course, the force of friction. Therefore, there is an acceleration because there is a net force. So this is Newton's second law, which is F equal ma. Alright, so in this tutorial, I'm going to solve a few problems. However, what I want you to do, I want you to give a try before you watch the tutorial. You only watch the tutorial when you get stuck. Free body diagram. You have to show all the forces acting on the body, number 1. Number 2, you have to show the velocity vector direction, acceleration vector direction, net force, and finally you have to explain the scenario, the problem represent Newton's first law or the second law. Remember, Newton's first law, the net force is 0. And Newton's second law, there is a net force. So let's get started. So first one, a rightward force is applied to a box. Alright, so let's draw a box. To push it across the floor. Okay, so there is a applied force. To push it across the floor. So there is a applied force with a constant speed. Alright, so speed is constant means the speed is constant means the acceleration is 0. That means that FA and FF balance out. Okay, don't forget to put the normal force and the gravitational force. They are equal in magnitude. I do not have room, so they are equal in magnitude. So Newton's first law tells us that if you use the Newton's first law, you will see that the Fn is equal in magnitude with Fg, but opposite in direction. So at the y direction, net force is 0. Fa, on the other hand, is equal in magnitude with Ff, but opposite in direction. So at the x direction, net force is 0. So the net force is 0. That means this is Newton's first law. The scenario number 1 represents Newton's first law. Let's move to the scenario number 2. Okay. Let me erase a little bit. Scenario number 2. A rightward force is applied to a dresser. So a rightward force is applied to a dresser. So rightward force. This is I'm going to call applied force. Okay? A rightward force is applied to a dresser. To accelerate to right. Oh, so this box is accelerating to the right direction. Okay. Across the bedroom floor. Okay. So acceleration is right. Velocity is also right. It's moving to the right. Force is also right. What do you know about force? You know about force that if you know the direction of the acceleration, you know the direction of the force. If acceleration is to the east, force is to the east. If acceleration is to the west, force is to the west. You know the direction of the acceleration, you know the direction of the force, because acceleration and force are the same direction. So then there is a net force. There is a net force. Then this one must be smaller. Then this must be Newton's second law. Alright, we are done with problem 1 and 2. Now let's do problem 3. Let's read it. A rightward moving car is skidding to stop. Rightward moving car. Okay. So rightward moving car. Be careful. Rightward moving car. Rightward moving car means velocity is to the right. Okay. A rightward moving car is skidding to stop. So then acceleration must be opposite direction, because slowing down and stop with a locked wheels. Okay, then the force must be that direction. Then there must be some net force. Okay, so the force is that direction, so there is only one force, so that is this direction, FF, and this is Fn, and this is Fg, and this is Newton's second law. Is moving upward. A football is moving upward. Okay, what does that mean? That means we have to draw a football. Good. And rightward toward the peak of the trajectory. Ignore air resistance. So we have to draw. First, check the velocity. Velocity is this direction. Upward and rightward. So this and this. Okay, velocity is this direction. Acceleration is this direction. So force must be this direction. Then there must be some net force. There's some net force. Okay, so net force is this direction. And that's it. That's it. So this is Newton's second law. Alright, number 5. The cabin of a small freight elevator is secured to a motor by a cable and moving upward with a constant speed. Constant speed means acceleration is 0. Let's write it down. Okay. So what are we talking about? A cabin of a small freight elevator is secured to motor by a cable, is moving upward with a constant speed, moving upward. F tension, Fg. Alright, so the velocity is up. Since acceleration is 0, force is 0. Okay, net force is 0. So Newton's first law. Okay, tension force is the force on the rope. Okay. Alright, let's check out the next one. A downward moving skydiver is falling with a constant speed. Okay. A downward moving skydiver is falling with a constant speed. So let's see. A downward moving skydiver, downward moving, so velocity is down. Let's put it down. Velocity is down. It's falling with a constant speed. Constant speed means acceleration is 0. Then the net force is of course is 0. Okay. If net force is 0, this is Newton's first law. If there is no force, there is no acceleration, and it's moving down, then a downward moving skydiver, then both forces are equal in magnitude but opposite in direction. Okay.